Okay, welcome. My name is Richard Parker, and I'm going to be sharing a little bit about Network Plus today. So I'm going to kind of walk you through, some information about Network Plus and share that with you. All right, so let's get started. We're going to look at the Network Plus N10-009, and we'll cover some network concepts, infrastructure, subnetting, routing and switching, network security, troubleshooting, network standards, and tools in this course. A little bit about me. I am a freelance trainer. I have a bachelor's degree in cybersecurity operations. It was part of a program for economic crime justice. I currently hold like 9 CompTIA certifications, 5 Microsoft, 1 Cisco, 1 cabling, and a splattering of others. Right? I'm an educator, so I'm always pursuing, but I also work in the field. I do not just teach. So let's get started. Let's talk about the exam a little bit. There are 85 to 90 questions. You need a passing score of 720, pretty much a C. You don't have to be perfect. What is the format? Well, mostly multiple choice. There are some performance-based questions kind of right out of the gate, and they will ask you to do something, to configure something, and you basically will just have to click the drop down and then click on the proper choice for what that configuration would be. For your multiple choice, most of them will be single answer. Some will be multiple answer. So make sure that you read the question really well, because right at the end it may flip it on you and go, which one of these is not a correct answer, meaning 3 of them are. Or it may say, choose 2 or all that apply. I always hate those because sometimes, especially like if it was a Microsoft exam, it could be all 4. So there are also maybe some drag and drop questions. And then again, your IE performance based. So let's look at some concepts like the OSI model, right? The OSI model has 7 layers. We have the physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. So when we look at these, what's going on? Okay, so the application layer, presentation, and session are the top 3 layers. We just call that data. Okay, when we get to the transport layer, or layer 4, then they're called segments, because at this layer it's going to break it apart and begin to break it into smaller portions that can then be packaged up and sent across the network or internet. At the network layer, this is our IP layer, where IP addressing lives, routing takes place, and we call these packets. Then that hands it off to the data link layer, or layer 2, and here we don't use IP addressing, we use the MAC address, and we call these frames. So traffic actually moves across the internet at the physical address from network interface card to network interface card. And then of course when we get down to the physical layer, where we put it on the wire or either wireless, it's just bits, right? Just 1s and 0s. So the OSI model, what is the function of each of these layers? Let me find my pen. There it is. All right. So the application layer, this layer is not the actual application that like Word or Excel or anything like that. This layer takes the basic information from that application and then encodes it into whatever the encoding is, whether that is like Unicode or HTTP, ASCII, whatever the encoding style is being used by that application. This is where it's going to convert it to that. When it hands it down to the presentation layer, this is now going to take whatever this encoding is and it's going to turn that into binary, i.e. ones and zeros. And so the encoding tells it when it gets to the other side what these ones and zeros mean. So a 1 could be a 1, it could be an A, it could be something else. So it tells it what it means. Then it goes to the session layer. The session layer will set up the communication, or as I like to say, the phone call. Okay? So it's going to establish the connection, and then it's going to hand it down to the transport layer. Now, the transport layer, it's going to package it up, but at the transport layer, this is where TCP and UDP operate. Is it going to be sent as a TCP IP packet, or is it going to be sent as a user datagram packet? Depends on what it is and what that application is. It's also going to set up segmentation, meaning packet 1, packet 2, packet 3 type of thing. It's also responsible for flow control, meaning how many packets can you accept at one time? If I send too many, it's going to bog you down. You're just not going to be able to handle it. So that gets negotiated as well. And most encryption takes place right here. Okay. Then it hands it down to the network layer. This is your IP layer. This is where routing takes place and routing decisions about how do I get to that place I'm trying to reach. Then it hands it down to the data link layer. So at this layer, the transport layer, we call that a segment. At the network layer, we call that a packet. It gets down to the data link layer, we're going to encapsulate that again, and now it becomes a frame. This is the MAC address layer, right? So this is where your MAC address works. There's some other things that kind of work between these two, like ARP, that resolves that IP address to a physical MAC address. And then it gets handed down to the physical layer. And down here at the physical layer, this is where it's put on the wire or wireless. And we just call this bits. So now it's just going to take that and move that across, okay? So that's what's happening at each of these layers. And when we think about what that's doing, then when we're troubleshooting at different things, we always look to what do we see happening and at what layer is that happening? That way I can drill down into what's going on. Okay, so there are two basic models. The first one really being the TCP IP model, which has been around forever. It has 4 layers. And the OSI model is more theoretical, especially for us network guys, where we can think about it a little more granularly, okay? So now there's some acronyms we can use to kind of help us to remember the OSI model. If you start from the top, all people seem to need data processing. Or some of my favorites like please, I come from the bottom, right? Please do not throw sausage pizza away. Or one of my favorites, please do not tell salespeople anything when it comes to networking, okay? Now, the TCP IP model, the application layer is the top 3 layers. It just doesn't matter, right, to us in terms of what's going on there. The host-to-host or transport layer remain the same. In the TCP IP model, we call that the internet layer, which is the same as the network layer or IP layer in the OSI model. And then with the TCP IP model, you have the network interface layer, which covers both layer 2 and layer 1. Now let's look at some of these things that are happening at these layers. With the application layer, you have Telnet, which today we don't really use. It's a no-no because it's a remote access tool and it's plain text. FTP is the file transfer protocol, probably the oldest protocol on the internet, really good with large files, but again, by itself is insecure. SMTP is your simple mail transport protocol. This is your mail server, right? This is not your inbox, but this is the exchange server protocol, right? So this is the mail you're sending out uses this protocol. DNS is the domain name system. This is how we resolve a name like google.com to an actual IP address. RIP is the routing information protocol. It was the first routing protocol we had. Operates strictly on hop count. There's some newer versions of that that now can allow us to use private addressing and things like that, and IPv6. And then there's SNMP, which is the simple network management protocol for managing our devices. At layer 4, right, we have TCP and UDP. Now we get down here to layer 3, or the network layer, which is our IP layer. You can see we got a couple different things operating kind of between the layers. IGMP is the Internet Group Message Protocol, and ICMP, or PING, right, the Internet Control Message Protocol. And then ARP. ARP is operating kind of between layer 3 and layer 2 because ARP is the Address Resolution Protocol. Basically says, I have an IP address, I need your MAC address, okay? There's also what we call reverse ARP, where I have the MAC address, but I need your IP address. So these protocols operate kind of between those two layers. And then down at the data link layer, we have Ethernet, token ring, frame relay, and ATM. Mostly today, we use Ethernet. There are still some of these other technologies that operate inside of different telcos and things like that, but most things today are all Ethernet. So let's look at a TCP header, okay? The header has a source port and a destination port, like port 80, right? So maybe it's coming from port 80 and it's heading to port 8080, okay? So it's kind of where's it coming from, where's it going to? Then there's a sequence number that was basically handed down from layer 4 that tells it what number packet this is in the sequence, so that when they reach the other side, it puts them back together in order. To give you an example, have you ever been watching like a YouTube video and all of a sudden your connection is a little wonky and it starts buffering and you get the little wheel going around, and then when it catches up, it starts back right where you were, okay? Because TCP is connection oriented. So you may have gotten packets that were received and they're out of order and it's waiting on packet 5, but it hasn't gotten packet 5, it got 6 through 10. So until it gets packet 5, it's just gonna buffer until it gets it, okay? And then there's an acknowledgement number. When you get the packet, your machine will send back a confirmation that it did in fact get that packet. If it does not, well, it'll do one or two things. If there's a problem with the packet, it'll drop it and ask for a new one. And because it's connection oriented, it will send you a new one. Or if for some reason it does not get the acknowledgement back in a specified time, it will automatically just send you another one. Then there's some other things like the do field, the reserve field, and the flag field. The flag field tells it what type of communication this is. Is it a send or synchronized request? Is it a GET request? Right. What is it? And then there's the window size. And that's basically the communication that was established at layer 4, like how many packets at one time can you receive or can I send you? Then there's the checksum. The checksum is a 16-bit hash, basically, of this header and the data and everything contained in this packet. So when you first receive a packet, the first thing your machine does is it calculates the checksum, rehashes it, and makes sure that those two numbers match. If they do not match, it will drop it and then ask for another one. And then, of course, there's an urgent pointer, depending on if you have quality of service and things like that configured, and then an option field, which generally is not used. That's why you see it gray. Now, you see all this information that's contained in that header. Now, let's look at a UDP header, or User Datagram Protocol. Notice there's a whole lot less information here. There's a source port and a destination port. Where's it coming from? Where's it going to? How long is this packet? Here's the checksum, and then there's the data. Now, there is a checksum, and it will, if it's a bad packet, it will drop it. But here's the thing. I always call this checks in the mail, because you asked for it, I sent it. If you didn't get it, that's not my problem, okay? We use this with real-time streaming services because it's fast, it's lightweight, and it gets through the interfaces quicker. There's less for that interface or a firewall to have to examine to make a decision of yes or no, okay? All right, so quick knowledge check. Which OSI layer handles flow control? Do you remember? Well, that's the transport layer. The transport layer handles flow control, or i.e. windowing size. Okay. Now let's think about some different network traffic concepts. A node. What is a node? Anything we plug into the network is called a node. It could be desktop, it could be a server, it could be a voice over IP phone, it could be a printer. Anything that we plug into the network is called a node. So what is a host? Well, a host is any device that's hosting other services that people are utilizing. So most commonly we think about a server, but it could also be a desktop. So if we were running in a peer-to-peer network rather than a client-server type of architecture, then every individual desktop has the ability to share its files with other desktops. So it could also be a host. A printer could be considered a host at times, right? Because many of our printers have the ability, I can walk up, plug in a USB that has some data on it, and then print it from there. So it could be considered at times a host. Then we have network media. So what is network media? Well, network media is cabling, okay? That cabling could be Ethernet, could be fiber, could be coax, right? Then we have networking devices. Networking devices could be or are routers, switches, access points, firewall can be considered a networking device because it controls traffic. You could throw in load balancer. All right, so these are types of networking devices. Then we have data. So data is the consistent of whatever that data is, being i.e. ones and zeros, okay? And then of course a bit is a single 1 or 0. And ones and zeros is pretty much it's either on or it's off, okay? We'll get more into those later and how they actually can play out. So here's a, picture basically of different networking components. We've got some desktops down here on the bottom. They are plugged into a switch. We have a server over here that's also plugged into the switch, so it's hosting services for us. We can see up here I have a firewall. This to the left is our modem, or i.e. border gateway router, right, connected to our internet service provider. Down here we see a bigger machine called a workstation. Typically they're much more powerful machines. They're type of desktop. It's a big tower typically that would have multiple hard drives. It could be running different services right in a dev environment. Then here's our wireless access point, providing us access for our wireless devices like laptops and tablets and phones. So this is just kind of a structured picture of how networks are built and how they operate. Now, what are some of the challenges? Well, availability, right off the bat. We always want to have high availability so that my users have access to whatever resources that they have permission to access. Security is definitely a challenge, especially in today's environment. Serviceability. What is my ability to upgrade or update that device? Some devices, most devices, are what we call mutable, meaning I can update them, I can access the source code if I need to, I can change some things. But some devices are what we call immutable, meaning they are what they are, they're monolithic. I don't have access to any of that code, I do not have access to be able to change it, it just is what it is. So it's not super serviceable. How reliable is my network? Are there things prone to go down, right? And if it does go down, do I have some form of backup, like for failover? Performance. What is the throughput capability that I have? How fast is it, okay? Or slow. Compatibility. So are my devices all compatible? If I add a new device into the network, will it be able to communicate with what I already have? Scalability. How able am I to add new equipment and either grow or even shrink the network when I need to, okay? So when I think about scalability, especially in terms of networking devices, 3 years from now, if I need to purchase a new switch to extend the network, will it plug in and be compatible with what I already have? Or do I need to replace all of it? Okay. And then what is my quality of service? So quality of service is when we start configuring QoS. We're guaranteeing bandwidth to certain devices like voice over IP phone. When you pick up that phone, it has to have a certain amount of bandwidth guaranteed to it so that you don't get choppy, broken communication, things like that. Now, network architecture or wired network topologies. The original was a bus. Back in the early days, and a bus was what we call half duplex, meaning I could either talk or I could listen. I could not do both at the same time. And we had some other challenges we'll talk about here in a minute. They were tried to be solved with a thing called a ring network, or the old IBM token ring, that was to solve some of the challenges of communication and throughput and stop what we call collisions. Then we got to the star configuration, which is typically what we see today. Okay, that's typically how we build our networks today. And then we'll talk about full mesh, which means every device is connected to every other device with a cable. And then partial mesh. Now, our bus network, or sometimes called a line network, meaning we have these devices, we got a single cable here, and these devices are all plugged into it, okay? And say this is computer 1, computer 2, computer 3, computer 4, computer 5, and computer 6. Computer 1 wants to send a message to computer 6. So it sends that message down the wire, but at the same time, computer 3 is trying to send a message over to computer 4, and we get this collision right here. And that was problematic, okay? And they first began to try to solve this with a thing called CSMA CD. That stands for Carrier Sense Multiple Access with Collision Detection. So it listened on the line, and when it heard, i.e. the noise of a collision, it would send that signal out. All the machines would run a back-off algorithm and wait, and then listen, and when the line was clear, they would begin to send information again. Another problem we had is if there was a break in the line anywhere, then it breaks that line of communication. And again, these were half duplex, meaning we could either talk or listen. We could not do both. And so they were slow, they were cumbersome, and there were a lot of problems. So the first iteration of trying to solve this was called the ring network, or IBM's token ring. And it used a device in the middle in here. I didn't really want that one, so let me do. Used a device in the middle in here called a MAU, or a multiple access unit. And it transferred, i.e. the token, you had to have the token in order to transmit. And it transmitted that token in a clockwise fashion. If you can think about when you were young and in a classroom, like elementary school, and you had to raise your hand to talk, right, or to ask a question. And so that is what this was built on. That was the idea that it was built on. And this allowed us to reduce those collisions inside of this ring. However, whichever one of these devices went out and plugged up to another device like a hub, well, anything going in that direction, you could have collisions. Okay, so we were still operating in a half duplex fashion, meaning we could either talk or listen. That was it. Then we got to the star network. So in order to solve the problem of the collisions, i.e. if you will, on that single line, like if there's a break anywhere in that line, anybody on this side cannot talk to anybody on that side, they came up with this device called the hub. Now a hub was just somewhere to plug stuff up like this. So again, it was still half duplex, and it just allowed me to plug in, right? So we could still have collisions, except if there was a problem with this cable, the only computer affected was that one. Okay, so it did begin to eliminate some issues, but still wasn't where we needed to be. Now, a full mesh. Now, let me back up for a second. So, well, we're going to get to a couple other devices here in a minute. We'll get to them in a minute, and we'll talk about them. All right, so full mesh. A full mesh looks at all of these computers, and they all have a cable connection to every other computer. This is the formula. N times n minus 1 divided by 2. So here we've got 6 computers. So we have 6 times 6, actually 6 times 36 minus 6 divided by 2. No, 6 by 6, excuse me. So we wind up with 36 minus 6 divided by 2. So we basically have 30 divided by 2 equals 15. So in order for these 6 computers to all be fully connected, there's 15 cables. And that becomes unsustainable. You would never do that in a desktop environment. Even though my little graphic has kind of desktops, we would never do this, right, in that environment. It's way too many cables. Now, a partial mesh. I do have multiple connections to different machines, okay? And this is our typical kind of backbone infrastructure, like for your core communications within the network. And it has multiple channels. So if one interface goes down, it has another path. But it's not fully connected. Every machine is not fully connected to another. And again, this would not be a desktop environment. This would be, our routing and switching environment. Servers right in the data center and those type of things. So let's talk about network scopes, right? Or how big is it? Well, a personal area network, what is that? That's going to be like your phone and your Bluetooth earbuds, okay? Or if you have a wireless keyboard and a wireless mouse connected to your desktop, it's considered a personal area network. Then there is the common local area network. That's everything inside the building, typically, right? It's under our control. Then we have our wireless network, or wireless LAN, which is just the wireless that's inside it. It would fall underneath. It would fall underneath, right, the local area network. Then we have this thing called a campus area network. So a campus area network is a bunch of individual networks. The easiest way to think about it is like a college campus. You got multiple buildings. Each of those buildings have their own network inside of them, but they all still fall under the bigger network, right? The local area network. Then we have the wide area network. The wide area network, the most easiest way to think about this is the internet. Okay? So we have the internet, and then we also have this thing called an intranet. Now, in today's environment, if you think about, you have a home office and you have branch offices. And today we used to use like either T1 or T3 lines, which were dedicated phone lines that we purchased, and they were super expensive. It gave us our own private communications between the home office and the branch office. Did it traverse the internet? Yes, but it did it in a way that it wasn't exposed to the wider internet. Today we use VPNs to create, i.e. our intranets, from site to site, if you will. And then there's this thing called the metropolitan area network. What is that? If you think about any city you live in, let's just take the United States, because that's kind of where I live, what I'm familiar with. Excuse me. Inside of a city, you might have the local phone company, and they're providing internet. You might have Xfinity. You might have AT&T. You might have Verizon, T-Mobile, right, and the list goes on. Each of these providers have their own separate, i.e. network, that you can, purchase their services and connect to. They're all inside of that one city, okay? So that they each have their network inside of that city, i.e. the metropolitan area, and it's called a metropolitan area network. Now, modulation and transferring data. From the beginning, computers have always been digital, okay? But the internet was not, because it was originally being transferred over phone lines, which were analog. So it would take that digital signal, and that's why we had this thing called the modem, and it would modulate that signal. It would take a sampling of this digital signal, and it would use a thing called the Nyquist theorem, and would calculate those bits, and then would convert those into symbols, and those symbols would equate to this analog signal. And if any of you are old enough to remember dial-up, those sounds, that's what was happening, okay? And when it got to the other side over here, this modem would demodulate or convert it back into a digital signal that you could use. Now, we took that same thought process, and I say we very broadly, okay? I didn't personally, but the industry took that same thought process and went, if we can convert a digital signal to analog and then convert it back, why don't we do the reverse? And that's how we got voice over IP phones, okay? And originally, if anybody remembers, there was a thing called Magic Jack, where you could make phone calls from your computer. And so it would take your analog voice, convert that to digital, and then send it, okay? And that is the basis of how we get voice over IP today. Now, a MAC address. Every device has a MAC address. It lives on your NIC card, or i.e. network interface card. Sometimes it's called a burned in address, because it is right in the actual encoding of that NIC card. Typically, if you look at one, it will have a sticker on it, right? So be kind of, have a little sticker on it that will have the MAC address, but it also is hard coded, right? So if you do bad things, yes, we can trace you. So let's look at this MAC address. The MAC address is actually a 48-bit binary number, and it is represented as mostly a 12-bit hexadecimal number, such as this, okay? It is broken up into two portions. The first portion, or the first 24 bits, is what we call the OUI, or the organizationally unique identifier. The second part, the network interface controller, is a number that is specific to you. You can think about, like in America, your social security number, right? Nobody else has that number but you. So therefore, that's how we can definitely track you, okay? Now, there are different types of MAC addresses beyond just the one on your NIC card, right? But the one on your NIC card, like this unicast address, so we have an example here of one that's specific to a device. Then there are multicast MAC addresses when we're doing multicasting, where, like if I was teaching this class live, I would be connected to a platform like Zoom or Teams or something that then would be sending that signal to whoever was connected on the other end, right? That's multicasting. And it would have a specific MAC address depending upon, that provider and things like that. And then there's the broadcast address. So the broadcast address is generally represented as all Fs. And if we looked at that in the binary, it would be 255, 255, 255, 255. This is actually dotted decimal that represents the binary. And what that means is that each one of these octets would be all ones. Right, so they're all turned on. Every bit's turned on. And that represents the broadcast address in general, okay? So when we look at the Ethernet frame format, it has a preamble, kind of like here comes some communication. Then it has this SFD, or the start frame delimiter, meaning this is where it's going to actually begin. And we have a destination address and a source address. Where's it coming from? Where is it going to? Then we have a length field that tells it how big it is overall. And then there's the data field. The data field typically is 1,500 bytes for a standard Ethernet frame. And then on the tail end, we have this thing called a CRC. You may also see it as this, FCS, frame check sequence. Both of those are correct. Do not confuse them. They're the same thing. And sometimes you may see in the test where they pose it one way and call it CRC, or they may call it an FCS, right? What this is a hash, meaning it's that 16-bit hash that looked at everything right here, took all of that, hashed it, and produced a 16-bit number. And so when it arrives at its destination, the first thing that machine does is take this number and rehash that again and make sure this 16 bits equals that 16 bits. They are not changed, okay? And that's really what we do with hashing mostly, is provide integrity, that nothing has changed along the path. Now, we were talking a minute ago about hubs, right? Hubs are a dumb device. They're just some place to plug something in. They operate at basically layer 1, and they didn't really do much for us, right? Still had collisions, still have duplex. They came along and introduced this device called a bridge. Now what that bridge really meant, let's draw some little diagrams here, is you had, let's say over here, I've got subnet number 1, and over here, I've got subnet number 2. In between them, I get this bridge. I'm connected here, I'm connected here. I got port A, and over here, I've got port B, okay? Inside of here, I've got a hub. And off of that, it's my devices. Over here, I've got a hub. And of course, my device is connected over there, right? So what this bridge did is it introduced a thing called a MAC address table. And that MAC address table would learn all of the MAC addresses that were over here, and it would say those belong to port B. And it would learn all the MAC addresses over here and say those belong to port A. So if I had a communication coming from over here and it gets to here, the bridge will look at it, it will check its MAC address table and go, oh, that belongs to go out port A. And it will send it out port A. And you got to remember, because these devices don't have any real direction, so any communication, even if it was meant to go inside of here, it will also still send, right, a communication that way. So the bridge helped momentarily. Today, this is called a switch. Okay? So we took that concept of this MAC address table and then created today what is known as a switch. And a switch is a smart device. Okay? So a switch, it has an operating system, it has a CPU, it has RAM, and it has that MAC table, right? So it has that MAC address table. What that means is if you have a device here, this computer, when you first plug it in and it plugs into this and it reaches out to get an IP address, this switch will now take its MAC address and it will add it into its MAC address table and go, computer 1 lives on port 1, and now it forever knows where you live. Okay? So any communication that's coming into that switch bound for this MAC address, it only sends it to that. So once we got to this point, we were now communicating in what we call full duplex, meaning I could talk, I could listen, I could do all of the above. I could walk and chew bubble gum at the same time, so to speak. Because this switch is a smart device because of its operating system, and it makes all of the decisions about how to switch that traffic. Okay? So quick knowledge check. What does OUI stand for? And that is your organizational unit identifier. That identifies who made this network interface card. Was it Intel? Was it NVIDIA? Who made it? Okay? So that's specific to who made that particular card. All right. Coax cabling. Coax, we can see that we have these, different types of cable. Originally, we had what was called thick net in the early days with, bus networks or line networks. We didn't have Ethernet cable. We had coax. And it was really slow, but that was replaced by thin net. And today, right, they use thin net, like with one of the cable companies, right? MediaCom or, Comcast or whoever. And so they have one type of cable that's running down the road, and then there's a different type that comes into your home, okay, a smaller one. And they can modulate and control, but these are your coax cables. And you'll need to know what they are, okay, for the test. These are your connectors. So the one on the right, this is called an F-type. Everyone should be familiar with that if you had a VCR right back in the day. They had threads and screwed on. And it was really important. You notice how the cable sticks out the end. That cable, when it's being built, if that copper coming out is too short, It won't get a really good connection. If it's too long, it doesn't want to tighten down right. Again, you don't get a right connection. You guys have probably all experienced this where you weren't getting a good connection. If somebody walk up there and just touch the cable on the back of the TV for a minute, it'd be like perfect reception. It'd be like, hey, don't move, stay right there, right? Because the cable wasn't necessarily built right. This one on the left is called a BNC connector. Stands for Bayonet Neil Councilman. Mr. Neil and Mr. Councilman are who created it. It's called a bayonet style because you push, twist, and pull. It's also known as a British naval connector because this is where it was first applied. Okay? So those are your two main coax, right, fittings or connectors. And we get to twisted pair, which is the most common, and we'll be using this till the cows come home, so to speak, forever, because it's cheap and flexible, and we use it everywhere. The most common is what we call UTP, or unshielded twisted pair, like here on the left. And you notice that these wires are color coded. They come in pairs, like green and white, brown, brown, white, orange, orange, white, blue, blue, white. So there are 4 wire pairs within it. Then there's STP, or what we call shielded twisted pair. And you notice it has aluminum kind of foiling around the pairs. So there's some where the individual pairs have the foil around it. There's some that's just around all 4 pair. But it's designed to stop interference from outside. Things like fluorescent lights, elevator motors, anything that generates some type of a frequency would interfere with communications on a UTP cable. So there are applications we would use STP, like if we're running across the drop ceiling, making a new drop, we would definitely use STP. And then there's what's called plenum. Now plenum, most cables, UTP and STP, they use PVC, or i.e. plastic, if you will, coating. And it burns really, really well and fast, and is toxic to you and me. It'll kill you if you breathe it. Plenum is not like that. It is a rubberized type of coating. If you've ever worked with anything like heat shrink, when you put the flame to it, it just kind of shrills and melts. It does not burn, it does not catch fire. And so this is used in high heat areas where, like around the HVAC systems and anywhere that's super high heat that could possibly ignite, you use plenum. But it is very expensive, and we only use it if we have to. Now, Ethernet wiring standards. This is showing to 568A. There's a 568A, and there is a 568B. A in the early days was your commercial standard. B was your residential standard. Not so today. Doesn't really matter because our switches today are even smarter, and even if the network itself was wired with an A standard, and you use a B patch cable to plug that desktop into the wall jack, the switch will recognize it, flip the signal before it sends it. Okay, so we don't really worry about that today. The difference between these two, now this is what we would call a straight through cable. But the difference between A and B is these green wires and the orange wires. Okay, so with a 568A, it starts with green, white. 568B starts with orange, white. That is the only difference, is where the orange and green wires go. The blue and the brown wires remain the same in both configurations. So the different types of cables, most common is straight through, and then there's a crossover cable. So a straight through cable would be what you would use like a patch cable when you plug up your desktop, right, and you plug it into the wall jack going to the switch. A crossover cable is very much about if you plug in two like devices, computer to computer, switch to switch, router to router, then you have to cross that signal over in order for it to communicate properly. And then of course there is a serial cable. Or a serial cable, what's also known as a rollover cable, is what you would use for a console. When you plug, like if you first deploy a router or switch, you're going to use a console cable and plug directly into that device and access it to begin to configure it. And so it literally reverses the wires, right, from one side to the other. Now, twisted pair connectors use an RJ45. And here's a couple examples, right? Telephone communications, especially the old analog, use what's called an RJ11. It looks exactly like this, right? So this is an RJ45. This would be an example right here of an RJ11, smaller cable, not as many wires in it. Okay, so here are your Ethernet standards. 10 base T. 10 base T was 10 megabits per second, used Cat3 and eventually Cat5, had a maximum distance of 100 meters. Then they finally got to what we called fast Ethernet, which was only 100 megabits per second. That was 100 base TX. Then that got pushed up to like 200 megabits per second. So that's 100 base TX. Then you get other standards like 100 base FX, 100 base SX, 100 base LX. Just keep this in mind. If it has a T anywhere in it, whether it's 100 base T, 1000 base T, whatever, that is twisted pair all day long. If it's anything else, FX, LX, SX, that is fiber, okay? Plain and simple. Now, fiber optic cabling comes in two flavors, multi-mode and single mode. Multi-mode can send multiple sources of light down it at one time. And that can either be, like at the top here, what we call a step index, or like in the middle, what's called a graded index. These fibers are made out of acrylic, or i.e. plastic, and they use LED light signaling. Single mode fiber, on the other hand, is actually glass, and it uses a laser to send that signal. Much more expensive, and both of them are about the size of a human hair. They do not like to go around corners. They have a very long, i.e. arc for a bend radius, which is why you'll never see them used in like desktop environment. Have to make too many turns in the building for it to be viable, and it's too expensive, right? So we'll always, you may have a multi-mode fiber backbone in your data center Typically, single mode fiber is long distance communication for like AT&T from town to town and things like that. Here's some examples of different fiber connectors. LC connector at the top, an FC, an SC connector, an ST connector. You will need to know and be able to recognize these connectors and what they look like, right, and where they apply. So definitely study those. Now, cable management. Here's a picture of an old 66 block. It was a 4-wire punch-down block. This was your old telephone communications. Not really in use today. You may still run across them in the basement of big, high-rise buildings that had analog phones back in the day. But they're not really in use today. But you do need to know what it is. But you notice there's nothing there to really tell you which wire goes where, right? You kind of had to know that. We use what is called a 110 block, okay? It is an 8-wire punch-down block. And you notice all the colors on it. I call this networking for dummies. It tells you what color wire to put where. So it does correlate, this punch-down block would then correlate to a backside of a patch panel, because on the other side, the patch panel is going to then connect from that to the switch. Okay, this is a BICS block. This is kind of Canada and Europe's pretty much Canada, 4-wire punch-down block. And here's the Chrome block. So this is Germany and Europe's 8-wire punch-down block that would be similar to the 110 block here in America. This is the front side of a patch panel, right? So the back side typically looks like this. Front side looks like this. So you would, these port numbers would correlate to what's on the back where you punch the wires down. And then there would be a short patch panel cable that would go from here to the actual switch. And that way, you kind of can track. You would want port 1 here to connect to port 1 on the switch type of thing, if you're doing it properly, okay? Here's an example of a fiber distribution panel down in the data center. So you see all the fiber up top and then coming in here, different colors depending upon what that particular fiber is and what the data is that it's moving. So you can kind of use different colors to help you in your management of it. Now this is what we call a media converter. You notice on the right it says UTP. This is where you're going to plug in that RJ45. And on the left, this is going to take a transceiver for fiber. So this converts a fiber signal either coming in to the building, and then it converts that to an electronic signal and sends that out, right, to probably to a switch from there, and then is able to be used in the network. So it definitely converts that fiber or the fiber signal, the light signal, into an electronic signal for communication. Now, fiber optic transceivers. There's SFP, or the small form factor pluggable. Then they got SFP plus. Then there's the quad small form factor. And then there's the quad plus, okay? As the speeds got faster. So this is an SFP transceiver. Your fibers would plug into here, and there's always two. There's one for transmit, one for receive, and then this thing would plug into a modular switch port, okay? This is an example of SFP plus. This is QSFP, right? The quad. So each one of these has, each of those two slots have basically two cables. And this is QSFP plus, and you notice that you have 4 of them right, that are coming in on one, and this other one actually has 4 cables that convert into that. So these are a couple of different examples of these, and again, they would plug into like a modular switch for fiber. These are some cable management tools. On the left, we have what's called a punch down tool. The little piece on the end comes out and flips over. There's 2 sides, one that's for the old 66 block and one that's for the 110 block. In the middle, we have a crimping tool for RJ11, RJ45, where we build cables. And then, of course, a wire stripper, right, to be able to strip the wire back and make it. Some other tools that we use for networking. Here we can see a tone generator, or what's also known as a fox and a hound, where we put the tone generator on one, and then we take this little tool to the right here, and we go listen for the signal on the other end, especially if you're trying to figure out, you've got some problems on the line from a desktop. So you would put the tone generator on the port on the wall, and then you would go into the telco closet where the punch down panel is, and try to figure out which one of these wires is the wire I'm looking for, okay? In the middle, we have an example of a multimeter, and then on the right, we have this thing called a cable tester. So when we build a cable, we can plug it into this and test it to make sure it's actually getting signal through and it's built properly, okay? Some other cable tools when we get into more advanced and expensive tools, like a time domain reflectometer and an optical time domain reflectometer. So one on the left is for, Ethernet, the one on the right is for fiber, and this is basically, we're going to send a signal down the line because somewhere in the wall there's a break in the line. In case you guys don't know, rats and squirrels love data cables. If you ever get one in the building, you will know before long, because you'll have some communication issues. And these are tools that you can send a signal down and figure out how far did it go down that cable before it was disrupted, and kind of get an idea where in the wall is the break in the cable. Then you have to make a decision of, do I tear a hole in the wall and fix the cable, or do I just pull a new cable? All right. So, quick knowledge check. What type of fiber uses LED signaling? And that's going to be multi-mode. Single mode uses laser light signaling. Multi-mode uses LED. All right, so I'm going to stop there, and we will get back to this in another video. Thanks.